This is video 2 from our lecture series for Friday, April 7th, where we now begin our next topic in our discussion of aqueous chemistry, where we are going to discuss stoichiometry in chemical reactions. Now, when we discuss stoichiometry in general, we are not going to be limited to just aqueous solutions or aqueous reactions, but we are going to spend a lot of time discussing aqueous stoichiometry coming up next. So this video is going to be kind of an introduction, an overview of what stoichiometry is in general for any kind of chemical reaction, and then we'll get more specific about solution reactions, aqueous reactions, in our next video. So let's start our discussion of stoichiometry in chemical reactions by defining what stoichiometry is. Now, I know that in chemistry there are a lot of weird words and element names that seem to come out of nowhere or seem to be random, so I'm actually going to break this down for you into your Greek roots. So this comes from Greek stoichion, which means element, and then we have metron, which means measuring. So if we put these together, then stoichiometry is the process of measuring elements. Now, when we talk about measuring elements, we're not talking about things like literally measuring the size of an element or something. When we say stoichiometry, the measuring that we're referring to is we're referring to the measuring of quantity. And as you might recall, the standard unit for quantity in the SI system is the mole quantity. So really, when we're talking about stoichiometry, what we're saying is stoichiometry is a quantitative process where the mole amounts of different substances are determined. Let's think about this idea of a mole amount, especially in the context of a chemical reaction. So let's ask ourselves a question. Where do these mole amounts come from and how are they used in chemical reactions? So there are kind of two pieces to this question. The first being, how are mole amounts found or used or given in chemical reactions? And then The second part of this question is kind of like, where do our actual mole quantities come from? Like, how are they calculated? So when looking at how to answer this question, we are going to look at information about moles given in some kind of chemical reaction. And we are also going to look at some kind of information about moles that is given by our actual reacted quantities. In other words, we've got to think about what I call the recipe for a chemical reaction, which is our chemical equation. And then we also need to think about the pantry, meaning what is it that we're actually putting together for our chemical reaction to happen. So let's kind of parse this out a little bit. Let's maybe break this up into these two aspects and make a decent distinction between them, because right now they seem to be described like to be kind of similar, but there is a little bit of a difference. So let's first start with the information about mole quantities that is given in chemical reactions or a chemical equation. So I'm going to title this mole relationships or ratios in chemical equations. So what kind of information about moles and mole quantities could we get from a chemical equation? So I'm going to start by making a statement, and that is that the coefficients in a balanced chemical reaction give molecular ratios that are needed for the reaction to proceed. So our coefficients are very important because these give us molecular ratios. So for example, if I were to look at the synthesis of sodium chloride from elemental sodium metal and elemental chlorine gas to make solid sodium chloride, I would need to, of course, balance this chemical reaction to ensure that I am obeying the law of conservation of matter. So I have one sodium atom on my reactant side, one sodium atom on my product side. So therefore, it seems like I am balanced so far with respect to sodium. However, on my reactant side, I have two chlorine atoms, and on my product side, I have only one. So I need to double the amount of sodium chloride that is made. And in doubling my chlorine, I have also doubled my sodium because I have doubled the compound quantity of sodium chloride. So in order to make this fully balanced, I in turn also need to double my sodium. All right. What on earth is happening here? So let's have sodium in red, and let's have chlorine in green. What is going on in this reaction? So this is saying that I need 2 atoms of solid sodium to come together with 1 molecule of chlorine that contains 2 chlorine atoms to create then 2 molecules of sodium chloride. So let's put this into language if this little diagram color coding system isn't helpful for you. 2 atoms of sodium are needed to react with 1 molecule of chlorine gas to form 2 molecules of sodium chloride. So just kind of a review of what these balancing results or coefficients mean. And the language that we use is for every 2 atoms needed, there is 1 molecule of chlorine needed for every 2 molecules of sodium chloride produced. And notice this language of for every this, there's this, that is a ratio. Now, how is it that this is helpful for us when thinking about stoichiometry, where we need to get mole amounts? So let's remind ourselves about this idea of atoms, molecules, etc. Atoms and molecules are generally what we call particles, and we know from Avogadro's number that 1 mole of a substance is 6.022 times 10 to the 23 particles of that substance. So let's say instead of looking at our reaction as an atomic or molecular ratio, let's scale it up so that we get a mole ratio. So we are going to scale our molecular ratios up to obtain mole ratios. So let's see here. I'm going to take all of these molecules, atoms, particle notation and replace them with this large quantity of particles. So I now have 2 times 6.022 times 10 to the 23 atoms of sodium reacting with 1 times 6.022 times 10 to the 23 molecules of chlorine coming together to form 2 times 6.022 times 10 to the 23 molecules of our sodium chloride compound. And remember, because we know exactly what this quantity 6.022 times 10 to the 23 particles is in terms of moles, I can now replace all of these quantities with moles. So I now have 2 times 1 mole of sodium coming together with 1 times 1 mole of chlorine to form 2 times 1 mole of NaCl, or simplifying by just multiplying our coefficients through these mole quantities, then we see that there are 2 moles of sodium in this reaction, reacting per every 1 mole of chlorine gas in this reaction to create, in proportion, 2 moles of NaCl. So we now have mole quantities expressed in a given proportion, meaning that in reality, while yes, our coefficients in a chemical reaction give the molecular ratios, we can also say that the coefficients in a chemical reaction also give us the mole ratios of each substance needed or made. So this reaction will only occur if I have a ratio of 2 to 1 to 2 moles of sodium to chlorine to sodium chloride. Based on this kind of atomic and molecular analysis here, scaled it up, we can now get coefficients giving us mole ratios. Now, in the earlier section of the notes here, I called this our recipe. So what is it that makes this the recipe? So when you're reading a recipe in cooking, a recipe tells you what ingredients come together and what ratios to form your overall dish that you're trying to cook. So for example, if we use a recipe for scrambled eggs, we might say that we need 2 eggs for every 1 pat of butter for every 1 teaspoon of salt for every 1 teaspoon of pepper. You would see this and say, okay, I need to have 2 eggs, this amount of butter, this amount of salt, this amount of pepper, and when I put these together in this proportion or in this ratio, then I will be able to form my product, which is scrambled eggs. So this is kind of like the theoretical guideline. This gives us what those ratios are for our chemical ingredients to come together so that we know how much of our product is formed. In this case, this would be a 2-egg scrambled egg dish. I'm going to break this video up into two. So in our next section, we are going to get into how we can get mole amounts from what we call the pantry here, or information about moles that are given by quantities that are actually reacted in the lab, meaning like what we have available to us. So we will continue this section of Intro to Stoichiometry in our next video, video 3.